cheater. Didn't do your homework.
It's due on Wednesday.
Yes, for the transfer part, and the one who asked if that's Laplace transform, you will need something like symbolic manipulation. All right. So hopefully we feel comfortable doing the first 3 steps towards getting to the transfer function g of s.
Yeah.
And the last step, so now we are at the point that I have x prime dot equals ax prime plus bu prime plus gamma b prime y prime equals 2 transpose x prime dx. Okay? Step 4 is Laplace transforms the result is an input output model, which will be that's the final result. So here's where we go next. However, there's an important implied assumption, and since we don't have text, I think I better not deviate too much from the notes, and as motivation of what we're doing, let's do a very ridiculously simple example. So, no, this is really ridiculous. So we're heading there, but let's do very simple example. So let's consider isothermal. So the control loop that controls temperature very well has already been designed this operational. Constant volume. CSTR with a simple reaction A with some, and now since it's isothermal, K includes the temperature dependence, okay? One way. Let's consider as measured output the concentration with a delay of 5 minutes. So we use for that the concentration. CA is measured with a delay the flow rate F is manipulated, and of course this is constant volume, that's both flow rate in and out. The flow rate in automatically equals flow rate out, automatically equals flow rate in. And the feed concentration normally has value. So when I say normally has value, what does that mean? What am I giving?
Nominal.
Nominal steady state. And I'm really helping out by making clear these are parameters. The parameter values are V equals 100 liters and K equals 0.1 minutes inverse, and the reactor is normally operated to achieve 90%. So we're going to use this example first to get there, to do a transfer function, and then we're going to generalize to the equation above. Probably not everything today, but we'll start. So before we start with the example, let's do a little bit of review of Laplace transforms. So you all had Laplace transforms in your differential equations class, right? Okay. The objective here is not going to be to do the derivations. I will give you the definition and certain important characteristics, and then I'll give you a dictionary. One side time domain, the other side Laplace domain. And basically we're going to be using the dictionary. But the Laplace transform is a definite integral that takes a function of time. It's a definite integral, so the t disappears and has a parameter s, and it's replaced by the parameter s. So by definition, the Laplace transform of a function f of t is the integral from 0 to infinity. If you want to be really precise, 0 approach from the positive side to infinity, f of t e to the minus the parameter s times t dt. So it's a definite integral. If you have integral of 5 st, let's say from 0 to 4 dt, what do you get? As a parameter, take it out, that's t squared over 2. So that's going to be 5s times t squared over 2 evaluated at 4 minus evaluated at 0. So that's going to be 5s 16 over 2. In other words, 40s. So this definite integral having the parameter s inside it changes 5t into 40s. So it's something that the result of that is going to be some function of the parameters. Just want to make clear that constantly you understand that's a definite integral. And s and this is a parameter, and therefore the result is a function of that parameter. And the other thing to observe is that it involves values of that function only at positive t. So whatever that function is for negative t is irrelevant. It only involves positive t. Important observations. Integral is a linear operator, which means that the Laplace transform if you take a scalar alpha 1 times a function f1 plus a scalar alpha 2 times a different function f2, that Laplace transform is equal to alpha 1 the Laplace of the first function plus alpha 2 times the Laplace of the second function. Okay. Same things hold if I'm talking about vectors. When I talk about vector functions, the constants in front can be matrices. So in multivariable situations, you have the Laplace transform of some matrix, let's say A1, times some vector function f1 of t, plus some matrix A2, times some vector function f2 of t, is going to be A1 times the Laplace transform of the vector function f1. And what does it mean, Laplace transform of a vector function? It means the vector for which every component is subjected to this integral operation. So that is the vector L of first component, L of second component, and so on. So that's the Laplace transform of the vector. So plus A2 L. Okay, so that's what it means, it's a linear operator. Error I don't want to ever see. Very important. Note. That's different from okay. A little bit about the inverse. The inverse takes us back to the time domain. It only pertains to positive functions of time. And it's also an integral. It's a line integral from your differential equations class. You remember that you used, remember that? But all I want to point out is that because it's an integral, an inverse is also a linear operator. And again, an inverse of products, it's going to be different. L inverse, right here, F1 bar of S, F2 bar of S, different. Okay. Then you have a question. My handwriting? So, for the purpose of this class, I'm giving you a dictionary, and I will expand a little bit from what I have in the notes about 2 more entries. So, I need the board space. I don't want to erase that part. So, and I definitely want to have the dictionary up there. So you'll allow me to erase the top board here.
What's the dictionary?
I'll just write it for you.
Oh.
Dictionary is something that translates, for example, from English to Greek, and back from Greek to English, right?
Well, I know what it is. I just haven't seen one in math.
Well, we have a dictionary between Laplace, the time domain, and Laplace domain.
Can you click the linear operator up?
Well,
Is that like an integral tables? Is that what you're saying?
I need to erase this.
Oh shit! Watch out. Felix, watch out. Felix.
Okay?
It was down here.
So this here is going to be our dictionary. If we have an entry that is very important because we'll be using it all the time, and we'll talk about some special cases of that entry. So I have here two columns. Here is time domain. Here is S domain. English, Greek. Okay? So, entries in English. Very important one. The following function, or here, let's put f of t, f bar. T to some power k minus 1 over k minus 1 factorial times e to the minus a t. So we have this function of time, which is essential polynomial, t to some power times e to the minus a t, and have parameter at the bottom k minus 1 factorial. If we go through the definition and everything, we can show that the Laplace transform of this function is going to be 1 over s plus a to the k bar. Okay. Some important cases for that. If we take the simple case where we have function 1. How do I get from this to be this equal to 1? If you take k equals 1 and a equals 0, what do we have? So this is what I get. K equals 1 and a equals 0. I get t to the 0, which is 1, over 0 factorial, which is 1, times e to the 0, which is 1. So this gives me 1. So what's the result there?
S.
1 over s. So the Laplace transform of 1 is 1 over s. That's a special case of this. How will I get t?
Something.
K equals 2. Right? This becomes t to the 2 minus first power. What's 1 factorial? Like 0 factorial is also 1. And a equals 0. So if you put k equals 2, what do you get? 1 over